Okay, we're starting chapter 7, which is on sampling distributions. So we're now moving into the second half of the course where what we're doing is called inferential statistics. So by inferential statistics, I mean we use sample data to make inferences about a population. So we have some population of interest represented by this bigger circle. And that population has a true population average, we call it mu, and a true population standard deviation, we call it sigma squared. The idea here is that we are taking samples of size n, and we're calculating sample statistics, those being x bar and s squared, the sample average and the sample standard deviation. So what we're ultimately interested in are these population parameters. We want to know information about these true population averages or variances, standard deviations. But I think we've talked about this before. It's not usually plausible or possible, feasible to sample the entire population. Again, think if we wanted like the average height of U.S. adults. Well, there's over 300 million people in the U.S. So sampling those people, everyone, just like wouldn't be feasible. And so we might take a sample of like 1,000 or 10,000 people and calculate an average there and use that to make a guess about the true overall population average. So we use the 10,000 people we sampled, and that's our best guess for the true population average height. So we call this the sample statistics. So we're using these sample statistics like x bar and s squared, right, such as x bar and s squared, to estimate those population parameters. They're our best guess for those population parameters. So these single value estimations is what we call a point, or we call this process point estimation. It's truly just one point. We get that one sample average, that one sample standard deviation. And these are our point estimates for those population parameters. And going through this whole process, and we're going to be expanding on this throughout the rest of the course. And this whole idea is what we're referring to as inferential statistics. We're trying to make inferences on the population, and we do that by taking samples. Okay, so we need to discuss the idea of a sampling distribution. So the sampling distribution. It's the distribution of values for a statistic if every possible sample of a given size is collected from the population. So let's talk about like what's really going on here. So there's a little bit of a process. So as we already discussed, we're taking a sample of size n from the population that has its true mean and standard deviation sigma. So we take that sample, size n. It could be any size. It could be 1,000, 10,000, 100,000. Using that sample, we calculate a sample mean, that being x bar, which we know is the sum of x's divided by the number of observations that we have. That's our sample average. And then we calculate our sample standard deviation, s, or actually that's a sample variance. I can fix this. This should just have a square root because I have standard deviation written here. And we know that this is our formula for the sample standard deviation. We practiced this back in chapter 3. Okay, so we took our sample, we calculate our sample average, our sample standard deviation. Okay, we then put those aside. We have our x bar, we have our s. So then step 3 is that we're just repeating steps 1 and 2 over and over again until we have a distribution of x bar values, and we call this the sampling distribution. So we keep taking samples, we keep calculating averages, and now all of a sudden we have like a bunch of sample averages. So if we took, say, 50 samples, I would have 50 x bars. And those 50 x bars would then have distribution, and we're calling that distribution the sampling distribution. Right, so we take the sample, calculate sample statistics, and then we just repeat that process. So we have all of these x bars, and that's what we're calling as our sampling distribution. So let's talk about some of these characteristics of the sampling distribution. First, let's discuss the mean of x bar. so the average of x bar. And we're lucky because the average of x bar, I'm going to call that mu x bar, is just mu. So in other words, the expected value of the average of our x bars is just the population mean mu. And that's a really good thing. So again, we took 50 samples. We have 50 sample averages. Okay, the average of those 50 averages, the expected value of that is mu, the population average. And because of that, we call it an unbiased estimator, or an unbiased estimate of mu. So x bar is an unbiased estimate of mu. And that's a really good thing, because mu is what we're ultimately interested in. So it's really great that if we calculate a bunch of x bars and take the average of those, we get an unbiased estimate of mu. Okay, and then the standard deviation of x bar. So the standard deviation of x bar, I'll call it sigma sub x bar just to represent. It's the standard deviation of the sampling distribution. And it's equal to sigma over the square root of n. So when you divide by a number, like a number bigger than 1, it makes the overall fraction smaller. So putting that into words, the dispersion of our sample averages, being the dispersion of our x bars, will be smaller, so smaller than the dispersion of the population data x bar, right? Because sigma over square root of n is going to be smaller than sigma, because dividing by square root of n is going to make it a smaller number. So we can take note that the larger the sample, in other words, the bigger n becomes, the smaller the sampling distribution, variance, or standard deviation. So we're just saying that this right here, or really, no, it's the same thing. This right here is going to get smaller the bigger n becomes. So if we take 50, like I said, we have these 50 sample averages. But if we then took 150 samples, that the variance among the 150 samples would be even smaller. And this makes some like intuitive sense, right? If I say collect up, let's say 10 people, right? I could have, say, 5 people above 7 feet tall. Like that's possible. It's unlikely, but it's possible. But that's not going to be a true representation of the actual population. Whereas if I take an average from like 10 people, I still might get a high average where like the average height is 6'5". But if I keep doing that over and over and over again, that eventually those estimates are not going to be subject to outliers nearly as much, because we're taking the average of the samples. And then as we do that repeatedly, we're going to see the amount of dispersion among those estimates shrink. And that's all we mean by this right here. So the next question is, how is x bar distributed? So we've been talking about the normal distribution. So to answer this question, we need to introduce the idea of the central limit theorem. So let's talk about the central limit theorem. Central limit theorem, or we generally abbreviate it as just the CLT. And it says that regardless of the shape of the population distribution, by population distribution, I just mean the underlying population, right? The whole, say, US population, regardless of how this here is distributed. If we take a large enough sample, so if we take a large enough sample, then the sampling distribution of sample means, x bar, will be approximately normal. And what do we mean by large sample? Generally, we mean n is at least 30. So this is a remarkable result. This is like one of the most key theorems in all of statistics. And it's pretty incredible because even if that population is not normally distributed, for example, it could be super skewed, but if we keep taking samples and taking averages of those samples, that distribution becomes normal, assuming our samples are big enough. So if we want to state this a little more succinctly, I'm just saying that if our sample size is big enough, that being n bigger than or equal to 30, then our x bars will be normal with mean mu x bar and sigma squared x bar, where we just define these as the mu of x bar is just mu. The standard deviation of x bar is sigma over the square root of n. So finally, calculating probabilities with the sampling distribution. So in the last chapter, recall that we transformed our x values into z values. And then we calculated probabilities using the formula z equals x minus mu divided by sigma. So we had z-scores, so then we could then look up probabilities using z-scores. We're doing the exact same thing here. But now we'll transform x bar into z, so transform x bar into z using this formula, where z is equal to x bar minus mu of x bar and sigma x bar. Again, using these definitions up here.